So we've got a problem of two asteroids in deep, deep space, so we don't have to worry about any other forces other than their own. And what happens is, of course, that they will have a mutual attraction because of gravity, and slowly but surely kind of come to a very gentle collision. And we don't want to figure out what's going on after the collision, but we have this A and this B, and we have now the total distance. So just before they collide, when the distance between them is RA plus RB, we want to ask ourselves, right, this is our after, what their speed will be just before colliding. So we're going to have this and this, right? We want to know VBF and VAF. So in order to start considering this, we want to think about the forces, what forces are external, what forces are constant, things like that. So we can kind of start asking ourselves, well, first off, are the forces constant? Well, we know what the force is. It's the force of universal gravitation. It's going to be G, MA, B over R squared, and we can do this negative R hat. So G is going to stay constant, MA is going to stay constant, and B is going to stay constant. But this R, we can see that we've gone from this distance down to this much smaller distance. So in fact, our forces are not constant, and we can't use that. So next we ask, are our forces isolated? If our forces are isolated, what that means is if I can consider a system, and a very easy system to consider would be one in which we consider just these two as our system, right, if we leave it like that. So if we consider both of the asteroids in our system, then yes, our forces are isolated. We can ask about if the torques are isolated. And if our forces are isolated, then our torques are isolated. Now, we're not going to use this one because we want to stick to a one-dimensional example. We only have so much time, only so much space on this whiteboard. But we can, right, take a look at that. And our last question we want to ask is energy conserved? After these two start colliding and start grinding and stuff like that, our mechanical energy will not be conserved. But our mechanical energy is conserved during the process of them going from here and colliding. So we can say that, yes, our mechanical energy is conserved. Well, what do we get from this? Well, we get from this, right, if we have our forces isolated, we have our momentum conservation. We have MA VAI plus MB VBI is equal to MA VAF plus MB VBF. Again, right, we're just considering the one-dimensional case. For torques, we can do an angular momentum version of this, but again, we don't need it. And then for energy, we would have, right, the kinetic energy initial plus the potential energy initial, so the kinetic energy final, plus the potential energy final. So in this case, then we can take a look at our momentum case. So MA, we know it. VAI, we know is 0, so we get 0. MB, we know it. VBI is 0, so we get 0, nicely enough. And then so we have MA VAF plus MB VBF. And so we can get, right, then bring one to one side. We have negative MA VAF equals MB VBF, or then we can say that VBF is equal to MA over MB negative VAF. Let's give ourselves a little bit more space and rewrite that. Cool. So we have a relation between VBF and VAF, but we don't know what either of the ones are, so then we have to go back and use our energy equation. So for our energy equation, we are going to take a little bit more space with this. Kinetic energy initial of A is 0, nicely enough again. Kinetic energy of B is 0. Kinetic energy of the entire system is going to be negative G ma mb over the total distance they have, which is capital R. On the final side, Kf is going to be 1/2 ma VAF squared. Mb is going to be 1/2 mb EBF squared. And then we have negative GMA MB over the total distance the centers are from each other, which is going to be a total distance of RA plus RB. So here we have two unknowns, VAF, VBF, but we have a relationship here, so we can substitute in our VBF is equal to negative MA over MB VAF. So every time we see VBF, we're going to replace it with that. So then our next step in here is going to be negative G MA MB over R is equal to 1/2 MA VAF squared plus 1/2 MB. And then, right, I'm going to square this so I don't have to worry about the minus sign because that goes away. The squaring MA over MB squared VAF squared minus G MA MB over RA plus RB. So here we can see that we have just one unknown left, right? We've used our two equations to unknowns correctly. We know MA, we know MB, we know R, we know MA, we don't know VAF, we know MB, we know MA, we know MB, we don't know VAF squared. We know MA, we know MB. Okay, so now we just have to do a little bit of solving. So one thing easy for solving is bringing this guy over. So we have this G MA MB over RA plus RB minus G MA MB over R. And then here we can then factor out the 1/2 M with the 1/2. We have this MA. And then here we can cancel out 1 MB with 1 MB here. So we have MA squared over a single MB. And we have VAF squared. So now we're just at math at this point. We can just take a calculator and plug all this in. If we want to do a little bit crazier, right, we can factor out this MA from this. And so then, divide everything. So then we would have G MA MB divided by 1/2 MA times 1 plus MA over MB. And then we have 1 over RA plus RB minus 1 over R. And this is equal to VAF squared. So we've done enough fooling around. Time to just get a number from this. So VAF is going to be then, through this calculation, 435 meters per second. And then we can use this, and then VBF is going to be negative 652 meters per second from that.